In this video, we're going to talk about how to implement a singly linked list. So if you remember, the way that a singly linked list works is we have a node with some value in it, and then it points to the next node in the sequence. Okay, and the thing that's important is that this data is not contiguous in memory. Okay, so when you see these pointers here, this is just like having an object reference to that object inside of the class definition. Okay, but like I said, this data is not side by side in memory. So if you want to find the value at, like if this is index 0, this is index 1, this is index 2, this is index 3, then let's say that, this is now null. If you want to find the value at index 2, you have to actually go through the linked list to find it. Okay? So the way that we represent this data inside of Java at least, is of course we're going to have some class, let's call it SinglyLinkedList. That is very poorly written, but hopefully you get the idea. And now we need a way of encapsulating the data that is one of these individual nodes. Okay? So first of all, we're going to make this generic, of course, because, well, there's no reason for it to not be generic, because then that means that we can store anything inside of these nodes. We can store numbers, we can store strings, we can store points, we can do whatever we want. Okay? But there's sort of an issue here. How do we encapsulate the information that comprises a node? Well, how do we coalesce information at all in Java? Well, of course, we use a class. Okay? So again, what information is this class going to have? Let's say it's called node. It is a generic object of type T, and we'll say that it stores a value of type T. And then it also is going to store what? It's going to store a node that is the next node in the sequence, okay? Because this arrow, of course, implies that if this thing is a node, then this thing is a node. And then this thing is a node down here, and then this thing is a node. And then if the next node is null, then, of course, it's at the end of the list, okay? So, but there's sort of another issue here. Do we really want to define a node class that everyone has access to? And what I mean by that is, let's go to our IntelliJ here and let's create a node class. Is there really so let's back up and think about the implications of doing this. If we do it this way, then anyone can instantiate a node object. But is there really a need for anyone to do that? Just like, is there any need for any arbitrary person or other class, for example? Is there any reason for anyone besides SinglyLinkedList? Is there any reason for anyone besides SinglyLinkedList to instantiate this node object? And the answer is no. So what we can do instead is, let's just get rid of this, and inside of the SinglyLinkedList class, we can actually define a private and static class called node. Okay. Now let's also make this the same type T here. So yeah. So there may be a question here. Well, what's the difference between a static class and a private static class? So the difference here is, let's say that this class has some properties. Like, let's say, so let's back up and think about what properties might a singly linked list have. A singly linked list might have the following properties. It might have, well, or I guess it should have, a pointer to the first thing in the list, which would then, of course, the first thing in the list is, of course, a node. And then each of these nodes, so we'll just say n for node, and we'll just say that there's 3 of them in some sort of sequence. And then this one we'll point to null. It also will have a last pointer. Okay. So the first pointer is for knowing where the list starts, and the last pointer is knowing where the list ends. Okay. And of course, like I said, both of these will be node instances. Okay. And we can also have, let's say, a size, so the number of elements in the list. Because, you may think, well, I mean, we can just compute the size each and every time, right? We can just go through the list and count how many nodes there are until we get to null. And yeah, that's true. You could implement it like that. But really, size should be a constant time operation. And what that means is there shouldn't be any loops or anything involved with computing the size, because that's very wasteful, right? We can just keep track of it in an instance variable, and then whenever we perform some operation that mutates the list, we can just increment or decrement the size. Speaking of operations, what kind of operation should this singly linked list have? Well, maybe we want to add an element to the end of the list. Maybe we want to set an element inside of the list at some index I. Maybe we want to retrieve the value at some index. Maybe we want to remove the value at some index. And maybe we want to insert some value at some index. Okay? Now, as you might recall, these are the methods that we wrote when we did the ArrayList implementation. Okay? And this is also why both linked list and ArrayList implement the list interface. Okay? The list interface has a bunch of methods, not just these, but what we could do is actually just combine all of these into an interface and then have our mini ArrayList class and our singly linked list class implement this interface. And then we could have a class, like, we can have a method, for example, that receives, we can call it like a mini list, and we could pass it either a mini array list or a singly linked list. And I mean, we could just call this a mini linked list as well. It doesn't matter. It's just sort of what I thought of when I started the video. I didn't think of mini linked list, so we went with singly linked list. Okay. It's also more descriptive than mini linked list. Okay. So we have these 5 operations, and unlike the mini array list example, we'll just say that all of these return void. Okay. So this doesn't return void, and this doesn't return void, but we'll say that add, set, and the insertion operations will return void. They will not return a Boolean value. So that also means that we're not going to do any type of bounds checking on these values. We'll just assume that they exist. Okay? And if they don't, then we'll assume that we're playing by the rules. Okay? But as an exercise, maybe you should go through this and add Boolean return values and check for correct, do the bounds checking. Okay? So now for the rest of this video, we'll just finish off the skeleton and the node class. But going back to what I was saying, this class could be static or it could be non-static. So why are we making it static? Well, let's think about the properties that this singly linked list class has. What properties does it have? Well, it has a node that is the first and a node that is the last. Okay? And then it also has a size. Okay? If this class were non-static, then inside of the node class, we could actually reference these instance variables in the singly linked list class. But there's no need to be able to do that, right? Why should singly linked list, or why should node have any knowledge of the first, the last, or the size properties of singly linked lists? And it shouldn't. Node should just be for encapsulating the state of a node in and of itself. Okay? Now, speaking of a node, what properties should it have? Well, it should probably have a final t value and a private final, or a non-final, and you'll see why in the second video, a next pointer. And actually, let's also make this non-final, and we'll exemplify why that is in the next video. Okay? So as for constructors, we'll have one that receives the value, and then we'll have another that receives the value and the next pointer. Okay? And then we'll just assign them over. And what we can do is inside of this constructor, we'll just call the other one with the value and null. So if we call this constructor, then that's like we're saying, okay, the next thing in the sequence is going to be null. Okay? Very good. So, great. So now that we've done that, in the next video, we'll actually implement all of the operations for SinglyLinkedList.